See, we're on this camera here. I'll try and get in the camera with you guys. Welcome to Hack Sunday. We have a very special presentation today. Anybody who hasn't been here before, welcome. We meet here every Sunday. We're just trying to, figure out AI, learn together, plus all the other stuff that you guys teach me. So I love coming here because I can just learn from people that are a lot smarter than me, and that's what we try and do here. Today we have a great presentation. We're going to learn about llamas and all sorts of stuff. And we're going to train our llama, find our llama. We're going to do lots of llama stuff. How to train your llama, yeah. Anyone who doesn't know the space, here we specialize, this space is really, Christina.
Come on, what's wrong with you?
This space is really, it's an intersection of art and tech. A lot of the art on the walls is from community members, and they have NFTs connected to it. So we're doing all different sorts of things here, trying learn and progress forward, whether it's on the medical side, AI, production. We're talking orcas. We're doing a lot of different stuff here. And so if you haven't gotten more involved, also we were talking about the different presentations. If you have something you want to present, please hit me up, DM me. We can get that set up as well. It does take some time and planning, so be prepared for that. And with that, I'm just going to turn it over to you guys. You want to give a quick little intro for people? We do have wireless mics. Please remember, this is their stage today. If there's something that you think should be addressed, just try and do it quickly. Let them have the floor, and we can do a whole Q&A at the end, too. On to you guys.
Hey, hope everyone's having a relatively good Sunday and so excited to be talking to y'all. And so excited to be talking here with Mr. Ken.
Hey.
Good to see you, bro.
Good to see you, man.
And Ken, I'm curious if maybe as a way to lead into some of this, you might say a little bit about your work using math and data to understand people.
Yeah, absolutely. So my background is in psychology. I full-time work at SpaceX in people operations. So I use people data, all sorts of different kinds, from surveys to sort of behavioral data that we could find in the different various platforms that we use and scrape from to predict various things like how good of a culture fit someone might be at a company, or whether or not they might leave the company soon. And I've worked with Stanley on a few projects to kind of do that similarly for the DAO ecosystem in Web3, kind of open sourcing a tool that we called Project Lion that was meant to learn about DAOs and create chatbots that are sort of digital twins of those DAOs that sound like them, talk like them, and also know the stuff that the organization knows, so that people can ask questions to that chatbot. Particularly helps with things like onboarding and finding information. If anyone's ever worked in DAOs, you know that information is just everywhere and it's really hard to find things. So if you could kind of sort of centralize it, it just really helps people in their day-to-day.
I can't believe you didn't share our acronym, Ken. How could you?
Lion was linguistic informatics on organizational networks.
That's right. And for me too, and just to share, have had the best time working with Ken. My career has been, the first part of my career orbited around building the computers to help these kind of scientists do their work. So when we met, and it was just around the time when large language models were happening, right? Or when we started talking about this.
GPT-3 had just come out.
No, absolutely. And so Project Lion, really cool open source project. And what we wanted to do is kind of put our data, all of our data about our lives and our organizations at the fingertips so that people could use it in training and creating their own large language models, right? And so that's the topic of our talk today, is like, how could you train a model that sounds like yourself or like your friends, or maybe even like your community? Like if any of y'all have like a really banger group chat that's always hilarious, you could have an AI that sounded just like that group chat. But anyway, without further ado, I'm going to kind of hand it over to Ken to walk us through our slides about how to train your llama.
Yeah, we're going to go through some slides today. The name's a little just trying to be funny. LLaMA is Meta's large language model that they've released open source to the wild. And it's been a really, really big thing for the open source AI community, and we'll talk a little bit about that too. But we're going to go through this talk. We're going to focus on the idea of fine tuning and how you train a model, but then later we're going to actually go through using something called AnyScale, which is a platform that allows you to use the LLaMA model among some other models that share similar infrastructure, and train it and chat with it and do really all sorts of cool things that you can do with large language models that are not super closed source like OpenAI is. The one benefit I will just say is that what's really nice about AnyScale is that it mirrors the way that OpenAI's API works. So if you're already working with OpenAI, you really don't have to change much other than importing a different client, and I think it's just changing the base URL that's pulling the requests from. So it's super easy if you're already working on something with OpenAI. You could just kind of come over to AnyScale.
Oh,
Cool.
Absolutely. And for anyone who is listening to this and is particularly gung-ho about training your model today, you might even want to navigate over to the AnyScale Endpoints website and get started with the process of creating an account. It doesn't take too long, but just while we're sort of flapping our gums, you guys can get started.
Yeah, and AnyScale they have their own API, but what's nice about creating an account is they give you $10 free. So everything you do today, I'd be surprised if you guys spent $1 because their best model, which is Mistral on there, is about 50 cents per million tokens, which is about 20 novels. So if you manage to spend 50 cents, I'll comp you today.
I'll be impressed. I'll be impressed. I'll give you the quarters. But yeah, and I will certainly flap my gums a bit about AnyScale because I'm an enormous fan of the company, and they maintain an open source software called Ray. Anyone who wants to do work in large language models should drop everything and learn Ray. I'm sorry to say something that emphatic, but Ray is, I think, what is used by all of the serious companies to do their training operations. So anyway, hopefully that'll be something cool we can all learn together too. But anyway, without further ado, Ken, I'm curious, what is a large language model?
So I kind of laid down a definition here that's pretty simple. I like to keep it that way because you can interpret what large language models are from a lot of different perspectives. But LLMs really they're computer programs that process and generate language. And it's really like LLMs are the answer to the question, what happens when you take all the text data on the internet and you throw it at a neural network? And this turns out to be what you get. And there's obviously a lot more technical stuff to that, having to do with the sort of architectures that are being used today and how we've been able to achieve what things like ChatGPT and other large language models look like today thanks to transformers, which is a type of neural network architecture. But really we're going to focus on, the idea of LLMs as you guys probably know them today, whether it's like ChatGPT or LLaMA, and most of those, I think all of those today, there seems to be some breakthroughs are going to be transformer models. So transformer LLMs are non-deterministic. That means they're stochastic in their processes. There's a little bit of randomness there, and that's something we could actually manipulate a little bit, and we'll show you that later. They're autoregressive. That also means that they predict the next word based on all of the previous words. They can't predict the third word without predicting the first and the second. They're scalable, and that's really important about LLMs because with the previous architecture, scalability was extremely hard. And what we've learned is something called scaling laws, and is that really scaling and the capability of scaling along with things like the attention mechanism, which maybe we could talk a little more about, is what allows LLMs to be so powerful today. And they're adaptable. They could really be used in all sorts of different processes, and that's because there's this little phrase that I like, that text is the universal interface, and really in a lot of ways it is. It's how we communicate with computers, and previously we've communicated with computers in deterministic patterns. We used programming that you could follow, and you knew exactly what it was going to do by reading it. But that's not the case with neural networks and large language models, and that's what makes them so adaptable to so many different use cases. And again, with fine-tuning, you could really get them adaptable to exactly what you need. And the last thing is, want to jump in?
No, go ahead. I was just going to say fine tuning. What's that, Ken?
We'll get into that in a second.
Ed might have had a quick too.
Oh, yeah, go ahead.
Yeah, so that's a good intro overview, and my question is related to the middle word, language. Can this be, what you're talking about today, apply to the other types of systems? I've heard of large action models.
Ed, thank you for letting me plant a question with you. I'm just kidding, but no, that's such a wonderful question, and I would love to address it. I was going to talk when Ken finishes, and maybe I could address it then. So maybe if you just want to finish the slide, then I'll interject.
Okay, perfect. Yeah, that sounds good. The last thing is they're latent learners. And what that means is, last week, for those of you that were here, we talked about this thing called embeddings. And embeddings is kind of really at the core of how these large language models learn. There's this sort of three-dimensional space called latent space where really what it is, its meaning is connected between different things. And large language models learn, or some people might say they understand, based on the different connections between meanings in that three-dimensional space. And this is also sort of how you could kind of compare and contrast large language models and neural networks to the human brain, and how we learn to make connections through various different things at different points.
It's, the kind of synchronicities between the things we see in these models and in our own brains, it's a very exciting time to be alive, you guys. And anyway, Ken put translation services on there, and part of the reason is that my first serious role as a research leader was as the principal investigator in machine learning for the group that did Google's language translation about 12 years ago, something like that. And this was way pre-LLMs and transformers. This was in just the very early days of hooking up multiple GPUs to work on the same problem. And we were using a technology called convolutional neural networks. And if you ever used Google Translate in the pre-transformers era and you saw it generate some really bizarre sounding stuff, that was a CNN. That was a convolutional neural network. Convolutional neural networks are beautiful for understanding the big picture, but then when it comes to the specific words and the way that they connect to each other and share the task of generating meaning, CNNs really can't do that. And just like Ken said, the sort of very specific word to word to word to word attention of understanding exactly how the words interact to create meaning, that is what LLMs were created to do and why they're so special. Anyway, so cool. And Ed's question,
right?
of course, forgive me too. And yeah, so then there's the question of like, they learn language, can they learn other things? Absolutely. And when you take, say, like a set of French data or perhaps a set of Spanish data, the data goes through something called a tokenization process, which is ultimately the translation of the sequence in an alphabetic form into a computer readable form, which ultimately is always just ones and zeros. And so it's actually incredible. Like if you train one of these models on Spanish and French, it will learn how to translate between Spanish and French and kind of understand the differences between those two languages. Similarly, if you have any other type of data that you can represent as a sequence, and you can feed that into one of these models, you can train the model to learn the data. So just as an example of something I worked on, Ed, which is fun, helped with the infrastructure for a model called Camberta, which is trained on sequence representations of chemicals and is now being used in the field of medicine discovery. It sounded like you were asking about actions, though.
Well, I've heard about it, like the Rabbit R1 has this large action model. It sounds like the key characteristic is sequential information. So whether it's a sequence of actions, it's a sequence of language, it's a sequence of X.
100%. And actually, I think as a further response to this, which is so cool, and again, the answer is a big yes. Like if you had a data set that had a juxtaposition of language and actions, you could absolutely train a model to both react linguistically or react with actions. Furthermore, I will share towards the end a really cool paper from a group I work with at Stanford. They took a video game system, similar to Harvest Moon or Stardew Valley, if you've seen either of those. And they actually embodied each of the NPCs with a large language model that had an action framework. So if you actually play the video of this community that they simulated with LLMs, you actually see like a number of the LLMs talking, and one of them says, "I'm hungry." And the other one goes, "Hey, I'm hungry too. We should go get a bite to eat." And then all the characters then return the token of like, "Oh, let's go to the cafe." And their characters walk over to the cafe.
So to follow up, things like animations. If you were animating a character, its behavior, it's sequential. It doesn't just jump from one point to another. It has a flow to it. So that could, in theory, be modeled with an LXM.
I love it. And I think I'm stealing LXM from you. That is too good. But no, 100%. And that is where, it's so interesting because like these things obviously have implications far beyond language. And then I would say something else is interesting because it came from language but has implications far beyond language, and that's the human brain. Most neurologists kind of believe that the increasing complexity of our language as we develop tool usage is what drove our brains to get so big. And so on some level, our brains are at their heart a language engine that learn to do more, and so we're kind of taking these early intelligences through a similar path of development. But anyway, Ed, such a good question, and can't wait to talk further after. But let me just move on and bring up that these models take a lot of work to train. It's literally on the order of 20,000 computers completely dedicated to training the model for 6 months.
Yeah, I think we have a slide that shows that coming up in a little bit on the number of GPUs. It's pretty nuts.
100%. And so I'm jumping ahead, but was just going to say, what they're doing when they're doing that work is they're adjusting something called the LLM's parameters. And Ken's going to tell us a little bit about that.
Yeah. So, the LLM parameters, they're really like the building blocks of the model's behavior, but they're sort of like, you can almost think of them as like the metadata of a node, or like the variables that that are being held in a node of a neural network. And as information passes through the neural network, each one of those nodes is using that to make a sort of slight tweak, an estimation based on what it sees, and that's being passed through the network in what's called a hidden state. And that's kind of like, the model is decoding information as it passes through, and then it's encoding it and passing it back out. And these parameters, they are the exact things that the training process is generating. And they start from a random state, and then as you train the model, they update through something called a backwards pass and gradient descent, which you might have heard of. And that's where you get to these things that are called base models, where they've now been pre-trained and they are pretty good at certain things, and you could use fine-tuning to make them much better at more practical things. So performance and scaling laws, something I mentioned before, generally more parameters is better performance, but there are some diminishing returns. I don't know if you have an opinion on this, but I think a lot of the diminishing returns that we see there have to do with the data itself as well. There's only so much data that exists in the world today, and the quality of data is super important. But what we tend to see as you scale up models to a certain point is that they start to fall off in performance, or what's called the loss ratio does not drop, which is kind of like the measure between how accurate the model is and how many errors it's making. And as that loss ratio goes down, you could kind of look at the quality of the data, and you could look at smaller models like the LLaMA model that we're going to work with today is, I think, 70 billion parameters, right, Stanley? But there are sizes that are 13 billion parameters, 7 billion parameters. And what we've seen over the last several months, maybe even a year, things are moving at crazy speeds, is that the quality of models is going up while their size is going down. And a lot of that, there's definitely different hacks that you could do through the training process. And there's these things called hyperparameters, which are not to be confused with the parameters themselves. Hyperparameters are external parameters that you can sort of adjust, not by the training process. And these could kind of get you different results. And what we're seeing is better quality data, smaller models, just as good results as the really big models. And I think we have now a 14 billion parameter Mistral model that is performing as well as GPT 3.5, which I think is on the order of GPT-3 here is, I think, about 1 trillion parameters or something like that. And over time, on this chart on the right, you're seeing how we started at a very low number. I think BERT, which is Google's model, is something like 100 million parameters. And now we're in the trillions of parameters. So models are just getting bigger and bigger over time, but we're at this weird place where we're finding efficiencies and they're also simultaneously getting smaller.
It's, that was so, can't believe any of this is real, y'all. I mean, was an AI scientist for a solid decade where you almost wanted to apologize for being an AI scientist because the tools didn't really seem too intelligent, It was kind of like funny how things have changed, how quickly things can change. And there's just one thing I wanted to kind of introduce, which is a visual for you guys, because when we're talking about parameters, when we're talking about all the parameters coming together to make the neural network, what does that look like? Well, I always like the idea of thinking about it as something shaped like a spider's web, where you have different strands that are kind of connected in a geometric pattern. And the places where strands come together, a number sits there. And that's what we're calling a parameter. So you could kind of think of it as this gigantic web. And it gets kind of fun, too, because if you actually imagine, what if you had the nodes an inch apart? How big would this be physically? And it's sort of covers the Earth multiple times, one of these large language models does. But then the way it has the intelligence and the way the intelligence manifests is you can almost think of it as like a fly lands on the web and it starts struggling, and then the vibrations spread through the web. And as they hit each of the nodes, the number that's there kind of changes how much the vibration passes to the next node. And so in the emergent intelligence and movement of this imagined spider web, that's where the intelligence lives. And I don't know, I think that's shocking. I think that's really shocking.
It's pretty incredible. And then you see, these things that we call, and I put them in quotes for a reason, emergent properties happen because you have these super large data sets and they're making connections that we can't really see. And emergent properties is a funny phenomenon because you could probably look back at the data set and do some deep investigation and kind of see, that's why the model was learning these things. But they're really emergent because they're really unexpected properties of training models and giving them so many different data points that they're connecting things that you didn't realize that they would connect. And I think there was an interesting example with Bloom on the translation side. Or maybe it was GPT-3, where it was translating languages that it had not been trained to translate.
Wild. And yes, that did happen. And then also to underline one aspect of why this is so important and exciting, and not just that, but the stuff that we're going to be doing together is important and is exciting, is we don't know how any of this works, y'all. Genuinely. The idea that the sort of geometric, kinetic, digital movement of this weird geometric object is intelligent or is interpretable as intelligent, we don't know where the intelligence lives, how it's stored, how to optimize it. And so something that Ken said, I just want to emphasize, we are at this moment where we're learning so much so fast. So 7 billion parameter models are popular because they will run on your MacBook. And so how intelligent we can make a 7 billion parameter model is a very focused area of research. And literally every month or two, someone finds a new 7 billion model that's significantly better than the last one. We have no idea quite how much performance we can squeeze out of a number of parameters. And not just that, but it seems like the most important thing is data quality.
Yep.
I have an example that I can share later, but somebody took a fine-tuning set of 50,000 examples, and they cut out 20,000 of them. and the performance of the model went up 20%. So the data quality ended up being significantly more important than the data quantity for fine-tuning. But anyway, let's talk about fine-tuning. Oh, wait, no, let's talk about open source LLM. I'm so sorry, I got the slides out of order.
Yeah, open source is really important to talk about when it comes to fine-tuning, because if it wasn't for open source, no one would be fine-tuning their own models. The only fine-tuning that would probably be happening would be, inside closed research organizations. And as unfortunate that is, we're super fortunate to be able to have open source models. And honestly, I don't know who the leaker was, but it could all be due to that one leaker of the LLaMA model, because I'm pretty sure the Mistral models are also based on the LLaMA architecture. And so what happened was, when I think it was LLaMA 1 came out, Facebook was not going to release it, and someone leaked it, and then Facebook kind of just owned it, and we're like, we're open source now on this. I mean, and to be fair, Facebook has been very open and open source with the dev community. They developed PyTorch, awesome library for training large language models, though you don't use it as much today because we have things like Hugging Face, which is listed here, which is, if you haven't checked out Hugging Face, probably the #1 LLM resource. You got to check out. Everybody posts their it's basically like GitHub for large language models. And all the new models get posted there. Leaks wind up getting posted there. And people, what's really cool is that the code that people use to train the models and getting them set up to do inference usually all lives in the same place. And there's just so many resources there. They have Hugging Face spaces as well, which people will build like mini applications from large language models, and you could just go play with them and then go and inspect the code and then do it yourself. It's just an amazing resource you have to check out.
Hugging Face is the shizzle, you guys, and we'll be exploring some cool Hugging Face tools a little later. But open source, one of the key things, we talked about imagining this big kind of tapestry of numbers that is the intelligence of the model. And saying it's an open model means you can download those numbers. And so I got them right here. This is a USB stick that I put the LLaMA models on the day after they were leaked, and I've kind of been carrying it around as a keepsake. And it's amazing because, think about it. This little thing, you can ask a question about anything, and it answers and knows more than almost any human. And it's something you can put in your pocket. It's really a miracle. Anyway, so that's so exciting. But then what is really exciting is if you have those numbers, it means you could tweak some of them, right, Ken?
Yeah, and I think that's what's really important. If we could just go back for 1 second, just one other point to make on open source, because there's a huge advantage of open source, and there's in AI today, there's a huge discourse going on that's really expanding from AI to becoming a political discourse on AI safety. And AI safety is super important. I think most people working in AI really believe in AI safety, but there's this fundamental idea that open source models makes AI less safe. And I think I used to believe that. And then I started really learning about them and using them and understanding that open source makes AI more transparent. It allows the sort of security engineering practices that have worked for us over decades, developers finding zero-day exploits and open source packages, is kind of the same paradigm that we now have today with large language models. Developers and communities could go in and they could crank these things open and they could play around with them and they could figure out new things. And they're both going to push the technology forward, but they're also going to find the ways where the technology can be dangerous, where a closed organization might not allow us to do. And someone who has that exploit could really tap into that without that closed organization knowing. And now today we have people that are able to crank into these things and find these issues, and then the entire field can correct them before they become a problem. So I think the transparency, the community support, and of course what we're about to get into, the customization, is what's really awesome about open source AI.
So Ken, tell me, what is fine-tuning, my friend?
So fine-tuning adapts a pre-trained LLM to specific tasks by further training on a small task-focused dataset, optimizing its ability to perform these tasks with higher precision. So what it's really doing is when you train a model, or I should say when you fine-tune a model, you're making it better at a particular use case, what's in that fine-tuning data set. So on the right, I stole this slide from Andre Kaparthi's talk on GPT-3. If you don't know who...
Love you, Andrew.
If you don't know who he is one of the greatest researchers in AI. He headed up Tesla AI for several years, and then went over to help out build GPT-3 at OpenAI. And this slide kind of describes the difference between pre-training, fine-tuning, and then reward modeling and reinforcement learning, the RLHF that a lot of you may have heard about, that makes ChatGPT kind of what it is today. And what's important about understanding this is that the pre-training process and the fine-tuning process are extremely different. Like I mentioned with starting off with a neural network, you're starting off from sort of like a random initialization of these parameters. And then you pass data through it, and you're telling the model, in the particular case of GPT-3 training, it's a sequence of words. It's going to be a full sentence, so it's a sequence of words, and then a masked word, one that will be missing, and then the rest of the sentence. And you say, complete the sentence, fill in the masked word. And it's going to do that really badly for a while, and then it's going to slowly get better and better and better and better and better until it is able to predict the missing word in the sequence. And then once it's able to do that, that is where you get to the autoregressive sense of GPT being able to predict the next word. And this is all probabilistic. There's something in the OpenAI API called logits, which you can manipulate, and there's temperature, which you could also manipulate, which changes the probabilities and which probabilities you want to select from. Upping the temperature is upping the randomness of the probability selection, so maybe you don't want to always select the top probability, maybe you want to select something more in the middle range, which kind of gives the model a larger distribution of things to possibly say. But what's important about pre-training is you don't get chatbots from pre-training. You just get basically document completers. So you may have some text and you're just saying complete the next thing. If you ask it, hey, ChatGPT, help me with this, it's just going to, probably it's going to repeat with this. Like, it's going to do that weird thing that anyone who's used GPT-3 early on, it would, kind of have this weird behavior like this. So they do this thing called supervised fine-tuning. And supervised fine-tuning, once the model is able to predict the next word, is you train it to complete certain sequences. So you have a prompt, which is maybe like a question, like write me a tweet about Chef Boyardee. I don't know, it's just coming to mind right now. I guess I'm hungry. And you're gonna fill in that completion with, what that tweet is. And then you give it a bunch of examples of that sort of thing, and the model learns that behavior. And you could adapt that to all different sorts of things. And it's very similar with digital twins, where it might be, write me a tweet in the style of Stanley Bishop, and then you take off Stanley's tweets and you fill those in there.
Man, so good. Both the slide, I'm like, wow, I'm going to steal that slide. And also the description, Ken. Thank you so much for walking us through that. Something that I would like to share is that it's really interesting to think about this as an educational process, the fine-tuning part, even more specifically maybe as a curriculum design process. So I sometimes like to think of and describe fine-tuning as giving a model its master's degree, which is kind of a cute thing to say, but then I think there really is an interesting comparison, because it's kind of like once you have your bachelor's, you've kind of been through training on the way to think, and you've been through your general ed classes, you've built kind of like a broad range of knowledge, and then the master's degree is to sort of specialize and prepare you to do a very particular type of work. So
that's a good analogy, because like people who go through graduate programs tend, especially if you go into the corporate world after that, you kind of realize, oh, people don't do things like we do in academia. And then you get RLHF'd into being a corporate drone if you stay too long. So that's kind of how reward modeling works too. It's like, now that you know how to do this, we're going to show you how we want you to do that in a very particular style. And RLHF is just kind of taking examples that the model has already completed. Maybe you take 3 different examples of the same prompt and you tell it, this is the one that I want you to sound like, and you give it a reward every time. And over time, it starts to sound like that style more often.
It's so cool. It's so cool. Yeah, very interesting. And then kind of cool to see too, like in the bottom right on that box there, where it's like notes for reinforcement learning.
And the
How many
GPUs on the bottom there.
How many
too.
GPUs required, right?
Yeah.
So how much does it take to do this fine tuning? Well, fortunately, it isn't the 50,000 GPUs you need for the pre-training. The reason why is if you picture that big spider web that is our neural network, you're not changing all the parameters. You're picking, let's just say, the parameters on the edge of the web. And if you think about it, if you change just those parameters, you can change very substantially how you would feel the wiggling of the web. And so it turns out that sort of like by working on just a smaller number of parameters, ones that could fit on somewhere between 1 and 100 GPUs, you can do this fine tuning and you can really substantially change operatively what it is like to interact with the intelligence of the model.
Yeah, and just to give some context here on how the growth of the field of AI is going, it was thousands of GPUs to train GPT-3, and I think at the time we didn't have H100s yet, but correct me if I'm wrong. Now, Facebook has just bought, I think it was like 350,000 H100s. So what kind of models do you think we're going to get in a couple years from that?
It's really like, I love history. I always like to look to history to understand my current moment. And there's a moment in history that I think of as quite similar to this one, which is like when people realized that if you had a cannon, you could knock down a castle wall. And kind of like our whole society was based on listening to the people who were in the castles for a long time, right? And so everyone sort of realized things were going to change, and then it was a race. How many cannons can we build? How quickly? And so the degree to which the economy has mobilized to get GPUs out there to support this kind of work is really something that'll be in the history books. I do hesitate to speculate on what Meta's going to get up to, though.
Yeah, so this is just a blow-up slide of what we're looking at if it was a little small before, but just kind of goes over what the pre-training process looks like, supervised fine-tuning, those prompt completion pairs, and reward modeling. And when you go from pre-training to this first supervised fine-tuning run, you're using a lot of examples because you really want a wide distribution. There's something called out of distribution, and models don't perform well out of distribution. And one of the reasons why large language models are so performant is because they're trained on so much of the internet that like most of the things we say and do online and the day-to-day work that we do, there's some blog post or tweet or YouTube video, because I think OpenAI scraped YouTube, and some information is out there on it. There's not a whole lot of things, unless you're at the real cutting edge of science, that there isn't some information out there on. So the vast majority of tasks, you're able to at least get some sort of guidance from ChatGPT on, and that's because we're training on this vast distribution of data. But if you get out of that distribution, that's where models tend to get really weird. So one example is if you try to use ChatGPT, and it's getting better at this, but if you try to use ChatGPT to call the OpenAI API, it's going to write the code wrong. And you're like, that's weird. Like, why would it write the code wrong? Like, that's what you're built off, right? But the thing is, the OpenAI API is not like, if you've looked at the docs before, it's not that great, first of all. And we've only been using it for about a year or two. So there's not a whole lot of data on using that thing. And when there's not a whole lot of data on something, there's not a lot for an AI to be trained on. And it's usually not that good at that thing. So that's where if you have a proprietary data set right now, the value is in that. Because if you could train a model on a proprietary data set, you could do something that no one else can currently do with AI.
Yeah, and so remember, guys, get ready for a universal basic income, and all that's left for us to do is generating novel data sets, okay?
So Kenneth, right?
Yeah.
So when you're saying that there needs to be a proprietary...
What is this, your first time here, Christina?
can't talk, proprietary amount of data in order to be effective, because if it doesn't have enough data, it's not going to come out with something good. What constitutes to be enough proprietary data to be effective, to be useful?
Well, for fine tuning, you actually don't need that much data because they've already done the hard, heavy lifting of the fine tuning process with the supervised fine tuning of, hundreds of thousands of examples of things that people might want to do with a large language model. But when you start to, if you have a particular use case that there isn't a lot of data on, there's actually ways that you could sort of prompt a model to give you the data set that you need to get started, and you could over time take those examples and start building a bigger and bigger data set and sort of optimize it towards the performance of whatever that task is.
Oh, so such a... No, go ahead.
So to clarify, if I want a very specific result, I just say, this is the specific result that I want. Now please train accordingly so I can get what I want. Thank you.
No, 100%. And listen, this is something we will be both talking about and doing after the kind of main flow of the presentation. We will actually probably be showing you guys how to train an AI that sounds just like Rick and Morty. And we will be using a data set that has about 1,500 examples of Rick and Morty speaking to each other. And so that actually should establish a baseline for what should be in your mind about how many interactions you need to train a model. And again, part of our idea is that you could go find SpongeBob scripts, or maybe the text message conversations with your parents, and then, but it's just so interesting too, because it sort of is a matter of data stewardship, right? Like us learning how to take the data that we have access to, that we have stewardship over, and then put it into action through these new incredibly powerful tools.
Stanley, I don't know if you want to touch a little bit on the project that you're working on with Stanford, but I think that's a really good example of how there's not a lot of existing data on interpreting some certain medical information, at least in the public sphere. And, it's not this crazy convoluted process where you need this super big organization with a lot of money to do this. You just need one person who kind of understands something pretty well. And if you can interpret some information and then sort of write a description, a detailed description for that information, you could then prompt GPT to say, here is, not prompt GPT, write a prompt and a completion pair that says, here is some information, here is a description of that information, which is your completion. So prompt, here is some information, and that information, completion, the description of the information. And you just do that repeatedly many times, and you could do this manually. It might take you a few hours, but you can do it manually, and even 100 examples is plenty to get going, I think.
Yeah, 100%. Very exciting, and absolutely always happy to plug our hackathon. And this is actually really a special time because we're launching a hackathon at Stanford Medicine this next week. And it's something that grew out of our work in this community here on supporting rare disease and sort of genetic illness patients who, as Ken said, in their own lives as patients deal with the out of data set problem, in the sense that most doctors have never seen most rare genetic conditions. And so they don't have both the informational or the interpersonal context to sort of meet the patient where they need to be met. So what we're doing is actually very specifically using these tools we're talking about in close partnership with the Stanford Medical Network of rare illness physicians to train, tune, and validate these models and kind of explore how they will be used in medicine to help patients. So anyway, it isn't just about having fun with your favorite cartoon show, guys.
So here in this slide, we're kind of talking a bit about both the fine-tuning process and digital twins. And I put them together because digital twins, I have the definition there, are really creating them is no different than any other fine-tuning process. The main difference is the data that you're putting into that process. And for a digital twin, you might have, like we just talked about, a Rick and Morty data set. So maybe your prompt is what Rick says, and then your completion is what Morty says, and then that is your Morty training set, and you just have a bunch of Ricks and then Mortys, and that's Morty's answer to it, and you train the model like that. So in this kind of a little more practical, concrete example on the bottom left, it's troubleshooting a login error. And someone says, hey, I can't log into my account. What should I do? And then the output is, I'm sorry, you're having trouble logging in. You can reset your password using the forgot my password option on the login page. So really simple. It's just what you want the model to say when you ask a certain question. You format those things together, and that is your training payload. And the other example I have here is, if you, just a little satire on Eliezer Yudkowsky, if you know who that is, he wrote the Time article saying that we should bomb the data centers if the AI gets out of control. So if your prompt is, write me a tweet in the style of Eliezer Yudkowsky about AI safety, it might be bomb the data centers as the completion. And then you do that a bunch of times and you'll get an AI that sounds like Eliezer Yudkowsky.
I have a favorite science fiction book, which is called A Fire Upon the Deep. And in A Fire Upon the Deep, it's the future. We have space travel and stuff. And there's like an intergalactic police that tries to keep people from creating dangerous AIs. So you have like kind of cops and robber simulations where some crew sets up on an asteroid to build a data center and start training an AI. Anyway, just Elizer's a funny character. But yeah, so this is fine-tuning. And then, yeah, using fine-tuning to create a twin based on a person and the evidence of their communication. And then these things are really interesting because I think we're going to be able to use these in a bunch of different ways, right?
A bunch of different ways. And I think, these are some of the things that we're starting to see now. But I think in the future, we're going to start to see really digital twins be involved in all interactions with AIs. I think part of making, any product, any technology to get a lot of use cases, iterating on user experience. And, even today, the user experience of ChatGPT, for example, is pretty good. I think there was some examples of research done on whether people preferred ChatGPT or doctors answering their questions, and they preferred ChatGPT. But this idea of having an AI that is sort of tuned to your needs specifically and kind of knows who you are and what how you like to communicate is just generally going to be a better user experience. And we're going to see these things in AR and VR, all sorts of digital assistants that are customized to the experience, personalized customer service agents that actually sound like the company and know information about the company, and of course AI companions, which we're seeing pop up everywhere. And it's going to enable AIs to make decisions like those organizations or people have the sort of emotional capacity like them. And even personalized learning experiences, I think, is going to be really cool, particularly because everybody kind of learns in a different way, and having the ability to have the AI understand that will be really important to, I think, the future of education. Do you have a question?
So you mentioned like this idea of digital twins with, say, a customer service representative that knows all the company's documents and can maybe look into a handbook and give information back. Would that kind of process happen at like a fine-tuning stage where you're feeding documents, or would that happen more at like a RAG stage? And how do you differentiate the two things?
Yeah. I would suggest, actually, there's an article I can share a link to that's kind of called if you Google this too, it'll just pop right up. But fine-tuning versus RAG versus both. So RAG is something called retrieval augmented generation, and this is actually a technique that we spoke about in recent weeks in the context of Gaurav's incredible talk on database technology, and specifically the idea that vector databases allow us to structure language geometrically in a way that a large language model can access. And so basically a RAG system lets us store an enormous amount of data in a database in a way where the large language model can use its intelligence to find the right piece of data. So for example, hey, John, are you here? Hey, bro, good to see you, sir. So we set up one of these systems with John's medical records, and John has, I think, coming on 2 or 3 terabytes of documents in a USB drive that he unfortunately has to lug around. And so you tell a large language model, I would like to see the sort of conclusion summary from John's last nanopore DNA sequencing report. And it would find it in the database, because the database is structured linguistically. The large language model can actually go out and find the exact thing, right? But then it feeds that return thing back into a prompt. And that could look like just maybe writing a little intro, like, hey guys, I found it, here it is, or maybe even interpreting it or saying something about it. So the actual finding of it and then allowing the model to kind of have a longer term memory, that's RAG. The actual way it sounds, the way it talks, the way it connects ideas, that's fine tuning. And then we actually get the best results when we do both, and not just when we do both, but when we fine tune with the intention of interpreting the RAG results in the best way. So the fine tuning will actually learn how to process, interpret, and integrate the results from a RAG. Such a good question. Sorry for jumping into the spiel, but this is kind of like my day-to-day technical thing, so the information is just stuck up there. I've said that a bunch of times in recent weeks.
Yeah, I think in the practical sense, it's absolutely critical at this stage because we have the hallucination problem. And when you need to build a model that does not say certain things or answer certain questions very specifically, you need a system to error correct that. But like Stanley said, when you have a good system in place, you could actually train the model to better answer those questions. And that's going to improve things like latency and all sorts of different use cases for the model, because it actually will learn to interpret those things. But as anyone who's worked in a corporation knows, those things change over time. So there's probably always going to be this fundamental interface of like how we are able to update this internal knowledge system that a model can then pull from and validate what it's saying before it kind of says it to you. And I think there was a funny example with, I think it was Chevy, who created a customer service chatbot that someone got to sell them a Tesla because they kind of prompted it in the right way. So like there's definitely a big use case for using RAG for cases where hallucinations is not something that you want to risk.
The Chevy example is pretty funny. I don't know if people saw this, but it's like the level of mistakes that were made in the construction of that model is like deeply embarrassing. And I feel that the meetings where Chevy met with a bunch of charlatans and set up the project to train that bot, the videos from that should be released as a public service so that other business leaders can avoid making bad decisions on team selection again. I'm sorry, I'm just being salty.
I was wondering, did they like poison it and put in with, and then use RAG, put in that data for Tesla before they went in and asked for it?
Lance, you're devious, bro. Oh my goodness. This guy.
I think they probably
Robber Baron over here.
I think they probably did. But that's sort of like the problem and why you need these retrieval systems, because not only do you need like the model to be able to access particular information, but you want like a sort of validation process in place. And something that I've done with digital twins before in the past is that, and right now this does sort of slow things down, but if you really, really need it to adhere to a certain set of rules, you might want to have like a check system where before it sends a response, it looks up to make sure its response matches what's in a certain set of rules. And that could be part of your RAG system where you're pulling in information on what cars do we sell? Oh, we sell Chevys. I'm saying Tesla. Maybe I shouldn't say that. And then fix that response before it sends it back in.
Yeah, and this gets into something called a DPO, or direct policy optimization, which is a more advanced and slightly different way of fine-tuning a model, not with prompts and responses, but with actual facts that it's supposed to know is true. So for example, when we're working with illnesses and there's maybe certain things that are dangerous to say to a patient, we'll use DPO to make sure it doesn't say those things. But anyway, this is so exciting. And then what's going on here?
Those are just some fun extra slides. There's a couple more there on the training process. If you keep going to, this one's not as fun, but this one's, interesting, the initialization process of it trying to complete Shakespeare, and the first time it's just random characters And then after 250 iterations, it kind of looks like a little more like, if you ever get one of those like template landing pages and it's got like the lorem ipsum, like stuff like that. And after 500 examples, it starts to have a few readable words there, and 5,000 examples, it almost sounds like Shakespeare. And then after 3,000, it's there. And if you go to the next one too, one more. This is how, when you are in the GPT-2, I don't think they did supervised fine tuning on. Maybe they did. I don't really remember. But you could get the model to kind of answer things, but you had to structure the prompt in a way where it was actually doing document completion, because that's what they're trained to do, complete the document. So this is where the term few shot examples come from, which, it's funny, we don't really do much of few shot prompting anymore. But before ChatGPT and before GPT-3 was instruction tuned, which instruction tuning is another style of supervised fine tuning where you have a set of instructions and then a completion. And it sort of kind of looks like this. You would few shot prompt. So you'd say, how old is Catherine? 54. Where does she live? And that's using the prior context to understand what the user is trying to get at. But if you had just answered that or asked that question without the examples, it would probably just produce gibberish, or, it wouldn't really give you what you're looking for.
It's so exciting and so fun to kind of flap our gums at y'all about this fine-tuning stuff, but who wants to maybe get us set up to do some fine-tuning? Does that sound fun to people?
Yeah. Let's do it.
Beautiful. Well, so what I'm going to do, guys, is I'm going to say just a little bit about this notebook and about AnyScale endpoints, and then we actually have a little bit of an announcement before we kind of shift into the ad hoc period of the day. But basically what I'm going to share is a Colab notebook that is fully set up to access a service called AnyScale endpoints. Myself, an enormous lover of AnyScale endpoints, I mentioned that they make a technology called Ray, which is the tool that is used by everybody working on this stuff seriously. OpenAI, Meta, just about everyone I'm aware of who runs a big shop uses Ray for key parts of the stuff we're talking about. AnyScale just doing such a service to the research community by making Ray available. And then they also have this service which is called AnyScale endpoints, and they basically set up a Ray cluster for you that you can interact with just by sending it your data. Setting up fine-tuning clusters is fairly challenging technically. As mentioned in the slide, it takes somewhere between 10 and 100 GPUs to fine-tune the bigger models. And setting up that many computers to work together is very challenging. The technical skills to do that are you're talking about the top 10%, 1% of machine learning scientists out there who know how to do that. So anyway, I love AnyScale endpoints, and I'm so excited to turn you guys onto it. This notebook I will share in just a second, but it goes through and explains the purpose of AnyScale endpoints to allow scientists, without dealing with clusters, to effortlessly scale your models. It can be used for rapid prototyping, scaling. And anyway, I just really encourage everyone to maybe go Google AnyScale endpoints and start setting up an account if you want to. And then in just a second, though, we'll share this notebook that has the example. This is what the first cell looks like. This is the initialization cell. So here you can see, like, you will need to, no one write down my credentials, okay? So block that out, block that out. You'll have to set up your own credentials. If anybody, for whatever reason, isn't able to set up credentials or doesn't have the kind of ability to do that, if you prep your data set, I will train your model on my account for free. But this is the cell that you run to connect to AnyScale endpoints, set up your tools, and then connect your Google Drive so you can manipulate data sets. Check this out. So here's actually where I am talking to a model on AnyScale endpoints. So you can see chat completion comes from client.chat.completions.create. And so this is part of what we imported right here. when we created the client object from the OpenAI API. And then as you can see, I have asked this model, how much wood could a woodchuck chuck? And the model has answered, how much wood could a woodchuck chuck is a play on words that has been used to tease and confuse people for generations. While a woodchuck may be able to move a small amount of wood if needed, the phrase itself is more of a clever play on language than a serious question. It's a fun and silly way anyway. It's good. And in this notebook too, when it's set up, you guys will be able to talk to some of your own models. And then this is all code too, so we can use this any way you can. You could, create 2 instances of this so 2 models talk to each other and you kind of feed the conversation back and forth. And if not for today, for maybe like fine-tuning presentation version 2, I'm actually excited to set up some of those systems. So maybe we can generate a Rick and Morty script by having Rick and Morty talk to each other. And then here I have some information, and this is stuff I think that will be better if we can kind of break out into little groups and work on together, because it gets a little bit more into some basic pandas-driven data manipulation. But we'll basically be using a really cool package from Hugging Face, our #1 friends in open source AI, to use a tool called the Datasets Library, which lets you basically grab a dataset that's fully set up to start working with and training a model with. And then in here too, I've put a link to a list of awesome Hugging Face datasets according to the community. So you can kind of go through there and see if there's anything that catches your eye that you'd like to work with on a digital twin. So like I said, I'll walk us all through this. And then when you get down to here, you'll see there's a little bit of a data frame processing that kind of puts the data set that I'm going to work with, that you guys are going to choose to work with, into the right form. And you can see that the form is sort of like, what question does the user have? And then what answer should the AI have?
If I could just ask a quick question. How many people have worked with the OpenAI API before? Okay, so it's about half the people here. Okay, so the idea here is that you always start out with a system prompt, and that's kind of the base instructions of the prompt for the AI and how you kind of want it to work. That's where you kind of could say things like, I want you to act like Leonardo da Vinci, or, write in the style of Stanley Bishop, or something like that. And then you have each step after that is telling the AI who it's talking. So you have the user, which is usually, you. And then you have that user's content or their question or their response to the AI. And then you have the assistant, which is the model, and that assistant's content. And that makes up what's your chat history. And each time that you send a new completion request to the AI, you are sending all of that chat history. So it has the context, and because it's a sort of like document completion technology, it sort of already knows that it's answering that last question. It understands the previous sequences, even though you're actually reinitializing the model every time you call it.
No, 100%. And gosh, I do have to say, I'm so excited to work on this, to experiment with it together, and I really do think this is getting to a place where I can get my creds out of this notebook, get it shared with everybody. And Luis, yes, sir?
I want to understand that comment better. Did you say it references our chat?
Oh, that's right. Forgive us.
Sorry, who am I asking that again?
I want to understand that comment better. Did you just say it references our chat history?
That's right.
And does that, for all models like ChatGPT 4, is it actually knowing, it'll talk to us knowing all of our chat history, or just that one conversation?
I don't know all the behind the scenes of what OpenAI is doing. What I can tell you is, for that conversation, it's going to know most of that history, and there may be some RAG in there, some retrieval augmentation to help with like longer conversations, but usually there is a limit there. That's called the context window. So if you're using GPT-4, I think that context window is about 128,000 tokens, so that's a big context window. If it's using 3.5, it can't go more than 16K, or it could be as low as 8K. So that really is going to shrink your context down. And if you have a long conversation, particularly if you're using like GPT 3.5, you might start to notice that it sort of forgets pieces of things that you previously talked about with it, and that's because those context windows are limited.
100%. Yeah, I think it mostly is the case that ChatGPT holds the context of the particular chat and doesn't cross-pollinate too much, although I think they might have a little stuff going on that, again, they don't talk about publicly. But anyway, so what we will be doing is getting this notebook to you guys, and then as able today, and then at fine-tuning version 2, when we do this again, we'll be helping you guys set up data sets, train models, and then we'll be talking to the models and kind of doing fun stuff with them. Once this cell that generates the training data runs, you simply go down to here, and then you create a fine-tuning job with this little piece of code. So anyway, we will share this with you. We will be present to work on it together, and I'm really excited about that. But before we do that, though, I think, is this a good moment for the announcement, you think?
Yeah.
We do have kind of a sad announcement to make, and it actually relates to this data set, because this week I was kind of working to get the Rick and Morty data set together with Michael Brooks, who is maybe the only bigger was maybe the only bigger Rick and Morty fan than me, one of my closest friends, and he passed away last week. Surprisingly, tragically, I'm so sorry to have to share that with the community. Mary, Michael's mother, is here to talk more and be present for the community to kind of understand what has happened. And Mary, if you're open, I would love it if you wanted to come up and say a few words.